Hello, okay, we're back, and this is the part 2 of the same presentation, week 8. So we talked before about the flame rod and photovoltaic cells, and now I would like to introduce you to the process of rectification. It's okay if you feel like this is a little bit complicated, but I would like to elaborate on how does it work and what is happening in a process of rectification. If you look at this circuit, this is here is a AC source, and you can see here this is a wave, sinusoidal wave, and this is what's going through the wire. If we go here, we see those which are diodes, right? So those diodes will be installed on the wire. So diode makes the current goes only one way, and this is, I'm not going to talk about this bridge, it's a little bit too electrical. We'll stick to the idea. So we will filter out whatever negative, because you know when we go in a sinusoidal wave, this is positive and this is negative, so the positive sign will go on one side and the negative will go on the other side. And as the positive side goes this way, we have a capacitor and a load corresponding to the capacitor to get the right impedance, and by doing so we have changed the system from AC to DC, where we have negative and positive. So basically we're shaving off these stops and putting it into VDC. I'm doing the same thing in the bottom. So this is, as you can see, is the resultant output in a waveform. So this is the simplest way to do a rectification system to change AC to DC, and probably you have that in your cell phone charger because you're plugging that into the wall and that's AC and you're getting DC. And the same thing goes also for some car transformers. I mean alternators, they have AC and they change that to DC and so on. So all you have to know is this is changing AC to DC in order, and we provide AC, and based on how much flames we have and ions we have, we will have some kind of indication of the intensity of. So what about the flame? So how does this, what does that do with the flame? So AC is applied to the flame. There's a ground applied to the flame as well. The flame rod will rectify the current and send only DC to the primary control. So if this is my flame rod and I'm applying AC to it, as the flame goes out, the ions here, the negative signals will unite with the rectification system with these charges and neutralize, and we end up here with DC with negative current. Based on how much negative currents we have, that means we rectified most of the system, and this can measure the intensity of the fire. That's putting it in a very simplistic way. So if you really want to read more into it, it's what is happening is actually the cathode of the rectifier is coated with active material, which has the property of emitting electrons whenever light strikes it, because we have positive charged parts. So only the negative charge are allowed to pass the primary control, just like I showed before. You don't have to know that, but this is the gist of what's happening in the rectification system. So that covers the flame rod. What about other infrared detectors? I mean other optical detectors. We said we have infrareds, which operate around 125, and they need a good view of the flame, otherwise they do not work properly. Ultraviolet, again, they should not be seeing the ignition. It's one of the properties, and they also need a good view of the flame. They all do. And also there's something you have to think about, is they have no tolerance for vibration, meaning if you're going to put it in a very close to the motor, close to something that vibrates, or a fan, it should not work very well, because any kind of vibration will distort the reading of those ultraviolet. So Honeywell company have a lot of rectification systems, a lot of flame rods, and a lot of controls as well. So we'll study some of the stuff that they have, because they are one of the biggest suppliers for flame detection in the industry. So we'll talk about specific wiring, mounting, location, insulation, and temperature, limits, and specific type of flame. So all these are required for are specifically required for each flame detector. So think about that as we go further and look into those rectifications. Photocells, flame only. Photocells is flame, infrared, gas or and ultraviolet is gas or oil flame. Okay, that covers up some of the general detectors we have. So we don't use cat cell anymore. We can use either a flame rod, we can use a photocell, infrared or ultraviolet. Now talking about the primary control. So before we had the cat cell primary control, we will have something a little bit more robust than that, and it does basically the same function, but it's an evolution with more controls, more options, and more sequence of operation. So it translates the input from the flame controllers limits into sequence of control to control the burner mode running, ignition, pilot, and main fuel valve. So it is very similar to what we did before, but now we have more controls and bigger valves to operate. So when we look at that in the lab, probably you'll see there are more components to primary control. So it started, if we look at the old ones, there are ones with completely mechanical and few relays that are completely mechanical. I like to have the comparison here between the car transmission evolution. Stick shift, automatic, was vacuum based, electrical with an overdrive using solenoids and using also relays, and now we have electronic and finally expandable gears. So they are improving a lot. If I have to follow up with the primary controls, they start with mechanical timers, mechanical relays, that went on to semiconductors, that went on with the single screen main controls, and also semiconductors, and now we have a whole processor, computer processor, that will control the boiler with a touch screen. So that's like the recent thing in primary controls. However, you will see the old ones still in operation, and it takes a long time for the underwriter laboratories to approve those primary controls and make sure they are not faulty and they are up to standard. So when we work with primary controls, we think about it as a black box. We do not disassemble or go in there because, again, it's something for the company who will take liability for that control and its function. It's primacy, so it's primary. And what we do is we have our controller, we have our limits, controller, limits, and flame signals, and our output will go again to the burner motor, ignition, pilot valve, and main valve. So we have two valves this time. We have one for pilot and one for the main valve, and we treat the primary control as a black box, and we do not look about what's going inside unless you are a technician who are trained to work with these controls, and they can be reprogrammed, and sometimes they have to be sent out and brought back again. What does it do? It provides a sequence of operation. It will pre-purge, meaning pumping air to empty the chamber. It will start the pilot, it will start the main flame, and it will do the proper timing for any of these operations. So it provides timing for all the functions, and it can be reprogrammed using small integrated circuit. This is what's called integrated circuit component. There are a lot of combination between resistances and capacitors, and basically they provide us with the proper timing and the proper circuits of operation to open and close circuits. So they can be wired to activate and delay. And again, this is not the recent. This is not the recent upgrade. The new ones completely, they have one processor, a computer processor that will do the entire operation. But this was a step up from the mechanical controls. Okay, one thing I want you to think about a little bit now, which is the ideal gas law. Why do we need to do that? At some point, whether in this class or in power plant, you will have to think about the ideal gas law and why do we need that. Okay, let me explain a little bit. What's an ideal gas first? An ideal gas is a gas that follows this law, which is pressure times volume equal number of moles, molecular weight of the gas, ideal gas constant, and the temperature. So we need the ideal gas law because we are dealing with steam, and steam at high temperature behaves like ideal gas. So what we need to know is the state of this PV over T coming inside a tube or a pipe will be the same, will maintain the same situation at state 2. So if we have a pipe and or if we're heating gas and gas is coming here at state 1, coming at 2, it will maintain this relationship, meaning if the pressure change here, something has to go down here to maintain this relationship. So this is a way for us to control and know what is the amount of gas or air coming inside or outside the boiler. I want you to know that before you go into power plant, because it will be very important for you to know how to calculate the flow rate of gases and the flow rate of steam. And it's not like fluid, because fluid is easy to calculate as volume because it does not change density. With gas, it's a little bit tricky, and you can compress and expand gases. So it's good to know the ideal gas law, and there's a question in the homework about ideal gas law where you basically fill in the other components to find the last one. So for example, if I have the pressure here, I have the pressure here, and I have the volume and the temperature, and I have the pressure here and the temperature, I can find the volume here. So you have 6 variables, with giving 5 of them you can get the 6 at any point. So it's a good way to calculate gas, volume, pressure, or temperature based on the previous situation. So just try to practice the math and going from state 1 to state 2, and this is the extent of what I want you to know in this regard.